Hello, good evening all. In these sessions, we'll discuss about how to calculate gyroscopic couple acting on a plane. Okay, so we have this problem statement. Aeroplane makes an complete half circle of 50-meter radius towards the left when flying at 200 km per hour speed. The rotor engine and propeller of the plane has mass 400 kg. Radius of gyration is 0.3 meter. The engine rotates with 2400 rpm in clockwise when viewed from the rear end, and we need to find out gyroscopic couple on the aircraft, and we need to determine its effect on plane. So you can write radius of curvature 50 meter, velocity 200 km per hour, convert that velocity into meter per second, just multiply by 1000, divide upon 36000, that is kilometer to meter and hour to second. So we'll get value 55.6 meter per second. The mass is given 400 kg. Radius of gyration is available 30 centimeter, that is 0.3 meter. Speed is available 2400 rpm. From speed, we can calculate omega value 2000 2 pi n upon 60, that is 2 pi into 2400 upon 60. So we have this value of omega 251 radian per second. Okay. Now mass moment of inertia we can calculate by taking I value mk square. M is 400 kg, k value 0.3 square. So m into k square, it will be 36 kg meter square. Then we have angular velocity of precession omega p v by r, that is 55.6 upon 50. It will be 1.11 radian per second. Then we have gyroscopic couple acting on aeroplane. I omega omega p. So we can put the value of I 36 kg meter square. Omega value we can put 251.4 radian per second. And we have that omega p 1.11 radian per second. By putting all these values, we have C gyroscopic couple acting on plane 10,046 Newton meter, that is 10.046 kilonewton meter. So in this way, we can calculate gyroscopic couple acting on a plane. Now it is asked, when aeroplane move towards the left, the effect of gyroscopic couple will be it lift the nose in towards upward direction, and it will tail goes in downward direction. That is the impact of gyroscopic couple on a plane when it is taking turn with clockwise direction of rotation. Okay. Now next part is what we have. Second question, just look at the next example. So this was the next question. Now aeroplane having mass of 500 kg, radius of gyration 30 centimeter. It is taking turn towards left. Okay. With radius of curvature 100 meter. The speed of plane is given 400 km per hour and engine rotates with speed of 3000 rpm. We have to determine the gyroscopic couple acting on a plane. Now again we can write mass 500 kg, velocity 400 km per hour, that is 400 into 5 by 18, 111.11 meter per second. K value 30 centimeter, that is 0.3 meter. Speed is 3000 rpm is given, radius is 100 meter. So you can calculate omega, uh, 2 pi n upon 60, that is 2 pi into 3000 upon 60. So omega value we have 314.15 radian per second. Then mass moment of inertia, I value we can calculate mk square, that is 500 into 0.3 square. So that value is 45 kg meter square. Angular velocity of precessions we can determine omega p v by r 111.1 upon 100. So that value is 1.11 radian per second. Gyroscopic couple acting on plane will be I omega omega p. So we have I value moment of inertia, mass moment of inertia 45. We have omega value angular velocity 314.15, and we have omega p 1.11 radian per second. By putting all these values of I omega omega p, we have gyroscopic couple 15,069.1 691.79 Newton meter. So that value will be 15.69 kilonewton meter. So in this way, we can determine gyroscopic couple for this case. Now we have one more part. Suppose the aeroplane is having mass of 400 kg, radius of gyration 40 centimeter, and it is taking turn towards left with radius of gyration of 50 meter. We have to determine speed of plane 200 km per hour is given, and engine rotates 2000 engines rotates with speed of 2400 rpm. We have to determine a gyroscopic couple acting on a plane. Now again, the mass is available 400 kg, radius of gyration 0.4 meter, radius is 50 meter. Then velocity will be 200 km per hour, that is 55.5 meter per second. Then we can calculate omega 2 pi n upon 60, 251.32 radian per second. I value mk square, that is 64 kg meter square. Mass is 400, k is 0.4 square. Angular velocity of precession is available v by r, that is 55.55 meter per second upon radius 50. It will be 1.11, and gyroscopic couple will be 64 into 251.32 into 1.11, that is 17,080 853.77 Newton meter. It will be 17.853 kilonewton meter. So in this way, we can determine gyroscopic couple acting on a plane for these various cases. Now, important task is, suppose say if you have these four cases, okay, we have discussed the different cases of aeroplane. Propeller rotates in clockwise direction, seen from rear end, aeroplane moves towards the left. Okay, just we are turning that axis. Okay, so these are the spin axis, precession axis, and gyroscopic axis. Just we have to turn that your thumb orientation towards left and right, and based on that active, if you have active in this direction, the active gyroscopic couple, then reactive will act in opposite direction. So based on that reactive gyroscopic couple, okay, active and reactive gyroscopic couple orientations, we can determine the position of tail end and nose end. So if it is this direction, then it will be in reverse direction, your reactive gyroscopic couple. So the tail end is going in downward direction, nose end is moving in upward direction. Similarly, if you look at the second case, okay, again we have propeller shaft rotates from rear end. If you take clockwise direction of that propeller shaft seen from rear end, and it is taking turn towards right. Okay, so look at the active gyroscopic couple. So this is the orientation of active gyroscopic couple. Again, we are taking observer. This is the observer position. Observer is looking from this side, and just we are turning that part, that is orientation of, we are turning that right hand thumb part towards right side with clockwise direction. So this is the direction of active couple. Reactive will act in opposite direction. So this is the reactive gyroscopic couple direction. So its nose is going in downward direction and tail is moving in upward direction. So these are the clockwise rotation with left turn and right turn. Now we have third part. If you take, instead of clockwise, if you take anti-clockwise direction of that rotor or propeller shaft when seen from rear end, what is happening? Again, we can apply that concept of right hand thumb rule. So this, and it is taking turn towards left. Okay, so just we are turning that thumb towards left side. So this is the direction of active gyroscopic couple, and reactive is acting in opposite direction. So its front end is going in downward direction and tail end is going in upward direction. That is nose towards downward side and tail is going in upward direction. So in this way, we can determine the third part. And we have fourth part. Suppose a propeller shaft rotates in again anti-clockwise direction when seen from rear end, and that plane is taking turn towards left side. So again, we have to determine the orientation. So this is the spinning direction. So we can apply right hand thumb rule, and based on applying that right hand thumb rule, we have this orientation of active gyroscopic couple. So just that turn that thumb towards right side. So this is the orientation of active gyroscopic couple, and the reactive gyroscopic couple will act in opposite direction. So just put that reactive gyroscopic couple direction on a plane. So you can see that tail end is going in downward direction and nose end is moving in upward direction. So these are the four cases for which we have to determine orientation of plane by putting gyroscopic couple, that is reactive gyroscopic couple, on a plane, so that one can find out the position of plane when rotor rotates in clockwise direction, anti-clockwise direction, and position of plane when it is taking turn towards left side and right side. Okay, so this is all about calculation part of gyroscopic couple, and determine the location or orientation of plane after implementing that rotor direction and plane turn towards left side or right side. Okay, so thank you all. We'll stop here.